All right, prop 4 says, if a straight line be cut at random, the square on the whole is equal to the squares on the segments and twice the rectangle contained by the segments. So this is a really cool one because it is a geometric proof of an identity that comes up a whole lot if you've ever taken a college algebra course. So we'll go through the geometry of it first, and then we'll take a look at what the algebraic representation looks like, the familiar representation. Okay, so in other words, what this is saying is that if we have some straight line, AB, I'll choose any point on it. I'll put it maybe, I don't know, right here. We'll call that point C. So, right, the claim then is that the whole square, the square on AB, would be equal to the square on AC plus the square on CB plus two rectangles that have side lengths AB by CB. All right, so how does Euclid prove this? Well, the first thing that he does is he says construct the square on AB. Construct ADEB, which is the square on AB. So I kind of have some lines that I tossed in here already. Hopefully they're going to be decently accurate. Okay, so there's our square ADEB. So first, construct it. We got a little pop up. Sorry. Construct square ADEB. I guess it's kind of implied, but that's on AB. And that was prop 46 back in book 1 that allows us to create squares. All right. Then once we have ADEB, Euclid says let's join BD. So it's the diameter. BD is the diameter of this square that we just created. Join BD. And then through C, we want to make a parallel, a line parallel to AD. So I'll say construct, what is it, CF, yeah. Parallel to AD or BE. It's the same thing. So just dropping a parallel down through C. Hits the opposite side at F. All right, right, and we need some kind of proposition. What was that? Prop. Let's see, he wrote 31, is that right? Let me just double check. I didn't look before this. Constructing a parallel through a given point to draw a straight line parallel. Yeah, prop 31. And then through G, so we'll call where CF intersects BD, we'll call that G. And through G, we want to construct a line parallel to AB. So maybe I should say let G be the intersection of CF and BD and construct, what do we call it? HK. HK will be parallel to AB and passes through point G. So this is G right here. I'll label it once I get my parallel in. Oh, it's a little bit off, I guess. Yeah, that's better. All right. H over here, K, and then right in here is G. There we go. All right. So the setup is all there. And we just need to prove that everything kind of equals what we said it's equal to. All right. So since CF is parallel to AD, and we have BD falling across them, we have that angle CGB is equal to the interior and opposite angle ADB. So CGB is equal to ADB. And that was by Prop 29. So angle CGB is equal to angle ADB. Right. But also, ADB is equal to the angle ABD. Why? Well, because we have that BA is equal to side AD. So ADB forms an isosceles triangle, and we know that the angles at the base of isosceles triangles are equal. So maybe I'll say since AD equals AB, angle ADB is equal to angle ABD. And that was Prop 5, yeah. It said something about isosceles triangles. Okay. Well, let's see, there's more. So those angles are the same. Therefore, the angle CGB is also equal to the angle GBC. So the side BC is also equal to the angle CG. So why is that the case? Why is CGB equal to GBC? Well, we had that CGB is equal to ADB. We have that ADB is equal to ABD, and CBG is the same as ABD. So since angle ABD is equal to angle CBG, it follows that. And I'll try to use the same ordering of the letters as him. Angle CGB is equal to CBG, or the way he writes it is GBC. Probably just to not be so confusing with the C and the G. This way he wrote it, at least, obviously, because Euclid wasn't using any of these letters. Right. And then kind of by the same idea, the isosceles triangles, so it's actually different. It's Prop 6. The isosceles triangles says that it's like the reverse direction, saying if you have a triangle where two angles are equal, then they are subtending equal sides. So for the same reason, so by Prop 6, we're looking at another equilateral triangle, in particular CGB. That's what we just proved, is that CGB is, not an equilateral triangle, an isosceles triangle. CGB is an isosceles triangle where CB is equal to CG, and that's what Prop 6 gives us. So, right. So CGB is equal to GBC, so that BC is also equal to CG. Yeah. Okay. But what does he say next? He says, but CB is equal to CB is equal to GK, and CG is equal to KB, because they're opposite sides of a parallelogram. And we can say that because that's how we constructed it. We constructed those sides to be parallel. So, and that was Prop 34 that tells us that opposite sides of a parallelogram are equal. So by Prop 34, we have that CG equals BK, and CB is equal to GK. But we just said, well, BC is equal to CG. So it makes, like, this is just a chain of equalities. So in other words, CG KB is equilateral. Let's see. Yeah, CGKB. Just trying to stay consistent with the Heath lettering. So CGKB is equilateral. And that doesn't mean that it's a square. It just means it's, I guess we would call it a rhombus. At the very least, it is a square, as we're going to prove. But we haven't shown that yet. All right, and yeah, that's what he says next. He says, I say next that this is also right angled. So we need to show that as well. Why is it right angled? Well, since CG is equal to, or sorry, since CG is parallel to BK, the angles KBC and GCB are equal to two right angles. So think of it like we've got these two parallels, CG and BK, and then AB is passing through them. So if you look at like the two kind of like angles that are being formed interior, we have a proposition that says that the sum of those is two right angles. So since CG is parallel to BK, we get that angle KBC plus angle GCB equals two rights. But by construction, one of those is already known to be right. In particular, KBC is a right angle because we constructed this as a square. So we know that KBC is a right angle. So it follows that GCB is also a right angle. And oops, so I should have cited this. What prop was that? It was prop 29. It says that those two angles would be right angles. Right. And then now that we've shown this, though, so we know that KBC is a right angle. We know now that GCB is a right angle. And then again, because this is a parallelogram, we have a proposition that says that opposite angles within a parallelogram are equal to each other. So, and that was, I believe that was prop 34 again, yeah. We get that the opposite angles, CGK and GKB, yeah. All right. So I'm gonna need another paper here. So what do we get? So we've shown now that CGKB is a square. So we'll just say that is a square. Yep. And we're starting to lag a little bit. So it happens, my computer starts overheating and the video lags a little bit behind the audio. So sorry about that. Right, so we've shown that this is a square. And it turns out by symmetric reasoning, we can use a symmetric argument to show that HDFG is also a square. All right, let's see here. Oh, he just shorthands it as HF. Yeah. It's also a square. All right. And in particular, I should say that, yeah, I guess I could have said this in the last one. So in particular, CK is the square on CB, and HF is the square, let's see. Yeah, is this is the square on AC, since HG is equal to AC. And again, that's from Prop 34. See, so it was a very clever sort of way of constructing this by only creating parallelograms, parallel lines, and then we can use all of these pieces to say, well, yeah, we know that like since AC is parallel to HG and AH is parallel to CG, Prop 34 says that the opposite sides are equal. So AC is equal to HG, and then HF is the square on HG. So really, since HG is equal to AC, HF is the square on AC, which is what we wanted. Okay, so yeah, therefore the squares HFKC are the squares on ACCB. Yes. Okie dokie. Now, since AG is equal to GE, and that one is not cited. Let's see if I can find that one really quickly. It's the one that says that complements are equal. Prop 43. Yeah. By Prop 43, AG is equal to GE. Yes, so AG is equal to GE. And then AG is the square on, or the rectangle contained by AC and CB. Why? Because we know that it's really the rectangle contained by AC and CG, but CG is equal to CB. So, but AG is contained by AC and CG, and CG we know is equal to, we've proven this, is equal to CB. So AG is, I'll say the rectangle contained by the segments. That's how it's listed in the proposition. Of AB. We'll just try to make it a little bit clearer. It's contained by the segments of AB. So let's see. AG is the rectangle AC by CB because GC is equal to CB. Therefore, GE is also equal to that rectangle. AG, yep. AG is contained by AC. And I'll just say, and so is, might be a little bit funny, and so is GE. GE is the exact same thing. GE is the rectangle contained by AC and CB. Right, therefore AG and GE are equal to twice the rectangles. All right, what does he say? And I mean, this is really kind of it. He just has like a little bit of cleaning up to do to say like, yeah, we've done it. But the squares HFCK are also equal to the squares AC and CB. Yes, we've shown that. Therefore, the areas HFCK, are equal to the squares on ACCB. Yeah. So just to kind of round this out, so I guess maybe the way I might write it is that AB squared is equal to CK, so the square CK plus the square HF plus AG, the rectangle AG, and the rectangle GE, which is equal to, well, CK is the square on CB, HF is equal to the square on AC, plus 2, and then we just stated AG and GE are both the rectangles of AC by CB. And that's what we needed to set out to prove. This is exactly what this proposition is saying, is that AB squared is equal to the square on the segments plus twice of the rectangle contained by the segments. Right, and that's really it, QED. So algebraically, what is this one saying? This is our old buddy, the binomial expansion on a squared binomial. So this is really this identity. Right? If you think of our square AB as being made up of AC which is side length A, and CB, which is side length B, you get exactly this identity. So there we go. That's one way of proving something that comes up a lot in college algebra, QED.